speed control. So let's talk about speed control in shunt DC motors. It's an important subject. So speed control can be done through a few methods. The first is, you saw how basically changing the IF could change basically your speed, right? The IF, if the effective IF is changed because of armature reaction, you can see that how it impacts the speed. So you can use the same concept to manually change the resistance inside the excitation circuit to play with IF in order to play with the speed. So that's the first method, changing the field resistance. So let's see how this works. So when you increase RF, or the resistance in the excitation circuit, IF will decrease. And we saw the effect of IF, decrease in IF was to increase the speed, right? So let's see. Decreasing IF will decrease phi. Decreasing phi will decrease EA, because EA depends on phi. Decreasing EA will increase the armature current, right? Now, increasing the armature current will increase tau. Why is it so? That's because, mathematically speaking, we saw that phi was decreasing, right? Here in tau, phi is decreasing in tau equation, but IA is increasing. So which one is dominant? Really, IA is dominant here under normal conditions. So overall, tau will increase. When tau increases, it will accelerate the machine, right? So that's why the speed will go up. But accelerating the machine will result in the increase in EA again, because EA depends on phi. Now, increasing the AA will decrease IA, which will result in decreasing tau. But that tau will be decreased basically to become equal to the tau of the load, because in the end, what is dominant in the system is the load, right? So it has to come back to the load tau again, because the system needs to get into balance. But that balance now is happening at a higher speed. So that's the point. So with the same tau, we were able to increase the speed. So that's through adjustment of the field resistance. So example, if IA is this value 2 amps, which is coming from 250, the terminal voltage, minus 245, which is coming from the EA, and this is RA. If phi is dropping by 1%, EA will drop by 1%, right? Because EA is chi phi omega. So EA2 becomes this much, 242. However, the armature current would be 49% increase. So that's why we say here in tau equation, IA would be the dominant, basically, component. All right? This was method 1. So changing the field resistance. So changing the field resistance. So we were showing the torque versus speed characteristics for 2 different RF values. When you increase RF, you're kind of shifting the torque versus speed characteristic, but you are basically also changing the slope of it. So that's the effect of increasing the RF if you plot the torque versus speed characteristic. Now, if you look at this characteristic in a larger scale, you can see that these two will intersect each other at very high torque values. Now you can see that the effect of these two gets kind of reversed, which means that this tau, which was k phi IA, now IA will not be dominant anymore. Now let's go to method number 2. Method number 2 is to directly change the applied voltage to the armature circuit. Okay, so if you have like a variable voltage controller at this point, when this does not exist, the changes of VT would basically be applied directly on the armature circuit. But we need that VT to feed our field, which we want it to be kind of dependent on VT. We don't want to change that IF very much, okay? If you don't want to change that IF very much, then you have to basically have some kind of controller in here, which kind of independently changes the VA versus VT, if that makes sense. So effectively, it's as if we are having a separately excited DC machine now, instead of a shunt DC machine. So putting this variable voltage controller is as if we are basically making the circuit of the armature independent from the circuit of your field. In other words, you're effectively making it a separately excited motor now. So if you have that means, which means that you could change the voltage applied to the armature, then how does that work? An increase in VA, if you increase VA, that will result in increasing IA. That increasing the IA will result in increasing the tau. Now look at here, tau is now having a constant phi element. That's because you're not changing the voltage applied to the field anymore. You just change the applied voltage to the armature. So that's why it increases tau induced. Increasing tau will cause tau to be greater than tau of the load. Therefore, it increases the speed, accelerates the speed. Now, increasing the speed will increase EA, same thing. Increasing EA will decrease the IA. Now, decreasing the IA will decrease the tau until the two taus become equal. The electromagnetic torque or the induced torque would be, again, equal to tau load, but now at a higher speed. That makes sense. So if you want to basically look at how this is going to affect the torque versus the speed characteristic, you can see that using this approach, you can, again, shift that curve or line, but without changing the slope. So in the previous, when you change the RF, you would change the scale. I mean, you would shift that line, but you would also impact its slope. But here, if you are able to change the VA only, you would shift, but you wouldn't change the slope. If that makes sense. So that's the impact of method 2, or changing the armature voltage. The third, which is the less common type of changing the armature resistance, that's also impacting the speed of the motor. However, it's not going to be used very much. So it means that you put an adjustable resistance in here, which you would increase. If you increase that RA, since IA is typically, especially under high loads, very big, then increasing the RA would increase the losses in the machine. Although it impacts the speed, but really it's not a very good idea to increase the losses in the machine. That's why it's less commonly used, but it impacts the torque versus speed characteristics, as you can see. So it again reduces or changes the slope. If RA becomes bigger, we would have a steeper, basically, slope, if that makes sense, which sharply basically reduces the speed. However, it causes basically some losses in the machine as well, which needs to be considered.
This example is talking about a motor, a shunt motor with these descriptions: 100 horsepower, 250 volts, 1200 revolutions per minute, with an armature resistance of 0.03 ohm and a field resistance of 41.67 ohm. The motor has compensating windings, so armature reaction can be ignored. Mechanical and core losses may be assumed to be negligible for the purposes of this problem. The motor is assumed to be driving a load with a line current of 126 amps and an initial speed of 1103 RPM. To simplify the problem, we will assume that the amount of armature current drawn by the motor remains constant. So this IA, whatever it is, and we will find that, we assume that it would be constant. So the question is, if the machine's magnetization curve is shown in figure 9.9, this figure, what would be the motor's speed if the field resistance is raised to 50 ohms? So initially, under these conditions, that the line current is 126 amp and the speed is 1103, the field resistance is 41.67 ohms. Now we want to basically raise this impedance to 50 ohms, and we want to see what would be the resulting speed of the motor in the second condition. And we're going to assume that this IA, which we will be finding out pretty soon, will remain also constant for the purposes of this problem. So the first thing that we should guess is that because we're going to increase the field resistance, we will be expecting the speed of the motor to also increase from whatever value is here, 1103. So we will verify that through this problem. So under the conditions, the initial conditions of the problem, IA would be equal to IL, the load current or the line current, minus IF, or the current of the field, which would be 126 based on the basically problem statement, minus 150 over this initial value of the resistance in the field circuit, which will give us a 120 amp value. And we would be assuming that this value would remain constant in the second condition of the problem, which would be the case that we're going to raise the impedance of the field circuit to 50 ohms from 41.67. All right, so under these circumstances, when the current of the armature is 120 amps, then we can find out the basically internal voltage or the armature voltage of the motor to be at Vt minus IA RA, which would give us a value of 246.4 volts. All right, so since we're assuming that this 120 amps will remain constant through this equation, we can also assume that EA1 would remain constant. So in the second condition of the problem, where we're going to raise the impedance from 41.67 to 50 ohms, this EA will remain also constant. So let's keep that in mind. All right, now we go to the second condition of the problem. When the field resistance is increased to 50 ohms, at this point, we're going to determine what the excitation current would be, which would be Vt. Vt is constant, doesn't change. That's the terminal voltage of the motor, over 50 ohms, which is the new field resistance, which gives us a 5 amps value. All right, now what we're going to do is to use the same famous equation of E is K phi A or K prime phi N. Since this equation should exist at all times, we can conclude that EA2 over EA1 should be also equal to K prime phi 2 N2 over K prime phi 1 N1. And K primes are constant, they just cancel each other out. Since EA1 would be also equal to EA2, since IA is constant, we just assume that based on the problem statement, then we would conclude that 1 would be phi 2 N2 over phi 1 N1. And from here, we can find out N2, or the speed of the motor in the second condition when the field resistance is at 50 ohms, to be equal to phi 1 over phi 2 over N1. Okay, now N1, we have it. We know it is 1103 based on the problem statement. Now, what would be the ratio of phi 1 over phi 2? This ratio comes exactly from this, basically the magnetization curve, because that's how the E, phi, and speed would be related. So in other words, since the value of EA on the curve are directly proportional to the flux, based on this equation, the ratio of the internal generated voltages read off the curve is equal or will be equal to the ratio of the fluxes within the machine. Now, we need to compare basically the EA at two conditions. The first condition is IF in the first condition, in the initial conditions, is 250 over 41.67, which becomes 6 amps. So that's why we're going to look at basically the 6 amps. The 6 amps is giving us basically the voltage of 268 volts from the curve. And in the second condition, when the field resistance is raised to 50 ohms, then IF in the second condition becomes 5 amps. And again, reading through the curve, we would see that EA would be equal to 250 volts. So from here, this ratio of phi 1 over phi 2 would be the same as 268 over 250 volts, which becomes 1.076. And the new speed of the motor is basically 1103 times this coefficient, which becomes 1187 revolutions per minute. So I've also done the same problem in MATLAB, and I approximated basically this curve using a few points. So this is basically how the problem looks in MATLAB. Now let's go to example 9.4, which is doing the speed control using VA, armature voltage. So when you're going to do the control using the armature voltage, you would be practically separating the armature circuit from your field circuit, and therefore it's as if you're practically having a separately excited motor, which is the topic of example 9.4. So in this example 9.4, we are reconnecting the same motor that was in the previous example as a separately excited motor as shown in this figure. And the motor is initially running with VA equal to 250 volts and IA equal to 120 amps here, and N equal to 1103, while supplying a constant torque load. So in this problem, we're assuming that we have the same load, constant torque. What would be the speed of this motor if VA is reduced to 200 volts? Now we are reducing basically the voltage of the armature from the initial value of 250 to 200 volts. So again, the first guess, or basically an intelligent guess, is that because you are reducing the voltage of the armature, then you would, with the same basically constant torque, you would expect basically your speed to reduce. That's verified. So this problem is also using the same parameters as the previous problem. So we're going to use them off in here. The motor has an initial line current of 120 amps and armature voltage of 250 volts. So the internal voltage in the first condition would be coming off of this KVL in here equal to 246.4 volts. By applying equation 916, which is the ratio of basically the internal voltages or the armature voltages based on K phi N. So we would get basically this to be equal to EA2 over EA1 to be equal to N2 over N1. Since K prime is basically the same, and phi 1 would be also equal to phi 2 because the field circuit has not changed. So there is nothing changed in the field circuit, IF, so there would be same phi, same flux in the two conditions. So therefore, N2 would be found from EA2 over EA1 times N1. And now in the second condition of the problem, when we are reducing the armature voltage from 250 to basically 200 volts, we can find out EA, or the armature voltage, or the internal voltage in here, EA, under these conditions, which would be equal to 196.4. So in this problem, you don't need to use the curve. You already have basically the information associated with E in the second condition and E in the first condition. And therefore, using that, you would be able to find out that the motor's speed in the second condition would be equal to 879 revolutions per minute. All right, now let's go to permanent magnet DC motors. So when we were in the previous chapter, all the time we talked about the stator as a permanent magnet, assuming that the N and S basically poles were present there. So in majority of the cases, those poles would be provided through an excitation circuit. But there are some cases that we would use permanent magnet for that. So there are some advantages associated with the permanent magnet DC motors. There is no external field circuit required, which eliminates the field circuit copper losses. Also, it has a smaller size because there is no requirement for field winding. It is ideal for small applications, which is common in fractional and sub-fractional horsepower sizes where a separate field circuit is impractical. But at the same time, we have some disadvantages for these permanent magnet DC motors as well, since they have lower flux density associated with the permanent magnets. If you really want to have a strong magnetic field, the solution is to go through an excitation circuit and not through a permanent magnet. And another important basically disadvantage associated with permanent magnet DC motors is that they have a risk of demagnetization. So what is that? So we know that there is a permanent basically flux existing in the permanent magnet. However, because of the armature reaction, we would be opposing that originating permanent magnet flux. So that there is a danger that the flux, the resultant flux gets very weakened. So high armature current can weaken or permanently alter the magnetic poles. So that's the problem. And also, excessive heating from prolonged overloads can also further contribute to demagnetization. Although we're calling these motors permanent magnet, but these permanent is not really permanent under basically extreme physical conditions, such as associated with excessive heating. So that's another disadvantage. Let's look a little bit into the magnetic properties of PMDC motors or permanent magnet DC motors. The armature reaction effect creates its own, because armature will create its own magnetic field. It can partially oppose the permanent magnet flux. This was something that we just mentioned earlier. The material selection for poles in permanent magnet DC motors would be associated with basically materials that have a high residual flux density, or BR, for strong magnetism. Also, we need a high coercive magnetizing intensity to resist the demagnetization. So what do these mean? BR, or residual flux density, is the amount of magnetic flux that remains in a material after an external magnetizing force is removed. So a high BR means the material retains strong magnetism, making it suitable for permanent magnet applications. So that's BR, the definition of residual flux density. And the definition of HC, or coercive magnetizing intensity, is that the amount of reverse magnetizing force which is required to bring the residual flux to zero. So if you have a high HC, it means that the material is resistant to demagnetization. So you cannot basically demagnetize it very easily. So in summary, we would need materials that have high residual flux density, or high BR, and high coercive magnetizing intensity, or high HC. Modern magnetic materials are like ceramic or ferrite magnets, and rare earth magnets offer better resistance to demagnetization compared to traditional ferromagnetic alloys, like Alnico 5. And rare earth magnets can maintain high residual flux while being largely immune to demagnetization. So this was just a summary of permanent magnet DC motors and the properties that they must have. In terms of speed control for PMDC motors, permanent magnet DC motors, since the flux is fixed, we really cannot basically change the flux very much to impact the DC motor's speed. Therefore, the only available speed control methods would be the armature voltage control and basically armature resistance control. So these are the two methods that are commonly used to control the speed of PMDC motors. All right, now let's go to series DC motors. The series DC motors, as the name shows, are configured in a way that the excitation circuit would be in series with the armature. So as you can see, here we have the armature, and this is the equivalent, resistance of the armature. This is our series, which is associated with basically the resistance of the excitation circuit, and this LS is representing basically the inductance associated with the excitation circuit. And the VT would be basically the terminal voltage would be at this point. So the load current would be the same as the series circuit current, would be the same as the armature current in this type of machine. And this is a very basically simple circuit, as you can see. So the flux would be directly proportional to the armature current. So this means that if the load changes, the flux would also change. As the load on the motor increases, the flux will increase too. So you can basically assume what happens, because basically the flux increases. So we would have some kind of behavior in this machine which would be different from the shunt motor, because in the shunt motor, unless we wanted to intentionally change the impedance of the excitation circuit, the excitation current would be constant, or the flux would be constant. But here, flux is changing with the load. As we saw earlier, an increasing flux will cause a decrease in the speed, right? You saw in the shunt DC motors that when we increased, let's look at the shunt, when we increased basically this resistance, then it decreased IF, which decreased the flux, which then increased basically the speed. So if you would want to have a comparison from there to here, an increase in flux would result in a decrease in the speed. So the result would be that a series motor has a sharply drooping torque speed characteristic. And it's shown in here as well. So you can see that contrary to the way that the torque speed characteristic would work for
the shunt motor, which we would be expecting something like this. Or in the case of basically a nonlinear, in the case that you had armature reaction, it would basically could go a little bit up and not sharply decreasing. But here in the series DC motor, you would have very sharp decrease basically in the speed as you are increasing. One of the advantages of this motor is that it can provide a high starting torque, which means that starting torque is torque when the speed of the motor is small or zero. So you can see that high torque can be provided at small or zero, basically, speeds. So let's look at the equations here associated with the machine, which are quite general. Tau in the machine, we know it's K phi I, IA, or the current of your armature. And in the linear region, we can assume that phi is dependent on IA. So that's the property of this, that is the characteristic associated with the series DC motor. Because the excitation current is the same as the armature current, in the linear region, you can assume that phi is C times IA. So from here, you can see tau induced would be KCIA squared. So the relationship between IA and tau would be changing based on the second power of IA. So let's go over these bullets. Also, the torque in the motor is proportional to the second power of its armature current. As a result of this relationship, it is easy to see that a series motor gives more torques per ampere than any other DC motor. So this is one of the properties of motors that people in industry can compare different types of motor. One of those would be the motor torque per ampere, how much torque can be provided through a certain ampere. And you can see that this value is quite high for a series motor. They're therefore used in applications that require high torques, as we saw it in here. Examples of such applications are the starter motors in cars, elevator motors, tractor motors in locomotives. Now let's go a little bit into the equations of the series DC motor. So we saw that phi was C times IA, and tau induced was KCIA squared. Through here, IA is found to be square root of tau induced over a constant. Kc is a constant. And we know that through this circuit, Vt should be EA plus IA times RA plus RS. So instead of EA, we put its equivalent in here. Vt would be, instead of EA, we put K phi omega. Instead of IA, we put its equivalent from here. And since IA is also equal to phi over C through this equation, the induced torque can be written as tau induced would be Kc over phi squared. So the same equation, tau induced, can also be written in terms of phi in here. Therefore, the flux in the motor can be rewritten as this equation 922. So if you solve for phi from this equation, you would get this equation 922, and then you can substitute that phi into a 921 in here and solve for the speed. So this is the math. The speed based on torque would get this characteristic. So in here, assuming that Vt, Kc, Ra, Rs are all constants, you can see basically the relationship between omega and tau based on this equation 923, which if you plot it, you would get something like this. So through this equation, you can see that if you reduce omega, if omega is reduced, this means that tau should be very high. So that's one thing that we can conclude from this equation. So when the torque on this motor goes to zero, its speed goes to infinity. That's another interpretation of this equation 923. Based on this, we should never completely unload a series motor. And we should never connect a series motor to a load by a belt or other mechanisms that could break. So we need to make sure that motor is always loaded. And if it happens that the motor becomes unloaded while running, the results could be catastrophic. So we should keep that in mind. The full load conditions of the motor operation would be something basically around this region. So this is the tau full load and omega full load. and you don't want to change this a lot. You don't want, because you see that basically the changes of tau versus omega are very sharp. They can go either this way or that way, which we want to keep the operation around this operating point. Let's go to example 9.5, which is talking about a series DC motor. In this example, we have figure 9.20, which is showing a DC motor with compensating windings. Total series resistance of RA plus RS is 0.08. The series field will consist of 25 turns per pole with the magnetization curve shown in figure 9.22. But one thing to note here is that the number of turns in the series motors, the number of turns in the excitation circuit is quite smaller than the number of turns in shunt motors. That's because the current in series motors is quite high. So an I that you would get, or the MMF is equal to the number of turns times the excitation current, would be very high with high number of basically turns. So you don't want that. Therefore, compared to shunt, because IF in the shunt motor circuit is smaller compared to basically IF in the series circuit, the number of turns in the shunt circuit should be higher compared to the number of turns in the excitation circuit of DC motors. All right, so in this motor, we want to find out the speed and induced torque when the armature current is 50 amps, and we want to calculate and plot the torque versus speed characteristics for this motor. Okay, so next page, I've brought the same problem statement here, just not to forget it. Part A, to analyze the behavior of the series motor with saturation, we pick points along the operating curve and find the torque and speed for each point. Notice that the magnetization curve is given in units of magnetomotive force. So one thing to note in this problem is that contrary to the previous problems that I can show you here, we were giving the V verse in terms of basically be in terms of IF, which is the excitation current. But here in this example, we're giving the E or voltage in terms of MMF. So MMF or F in ampere terms. That makes sense. Okay, so let's look at this. For IA equal to 50 amps, through the circuit of this machine, we get basically EA to be equal to VT minus IA times RA plus RS, which gives us a 246 volts. And since IF is the same as IA, when IA is equal to 50 amps, the basically magnetomotive force would be 25, which is the number of turns, times 50, or 1250 amp turns. Now, from the magnetization curve, if you go over 1250, you will see EA to be equal to 80 volts. So 1250 would give you, it would be something around here, which is around 80 volts from that curve. To get the correct speed of the motor, remember that we always had this equation. So the EAs, or the armature voltages, would be corresponding to the ends or the speeds. So therefore, based off of that, you can see that now that the actual armature voltage is 246, comparing that to the 80 that we got in here, it means that this is 1200, not 120. Then that speed becomes 3690 revolutions per minute. Okay, so that was the solution to part A of the problem, find the speed when the armature current is 50 amps. So we can use the same process to calculate and plot the torque versus speed characteristics of the motor. So we know that basically P converted would be equal to EA times IA, that's the converted power, which would be equal to tau induced times omega. And from here, basically you can find the tau to be equal to EAIA over omega, which gives us 31.8 Newton meters. So using this concept, same process, you found basically we can find the speed as well as the torque for different operating conditions. If you change IA was 50 amps
which gave us these two values. Now, if you change IA, you can plot the torque versus the speed characteristic, which would be something like this. Now, I have done that in MATLAB. Basically, I've given a function here, which gives MMF, which is called MMF-EA, basically gets the MMF and gives out V. And through this, we've been able to go through the same process and be able to get pretty much the same torque versus speed characteristic. Now let's go to control of speed in series DC motors. The only efficient way to change the speed of a series DC motor is by adjusting the terminal voltage. That's because the motor's operation could be very much impacted if you change basically the excitation circuit's resistance. The effect of the terminal voltage would be that increasing the terminal voltage would increase the motor speed for a given torque. So if there is the same torque, when you increase the terminal voltage, that would increase the speed. An alternative method, which is inefficient, would be controlled by inserting a series resistance. Okay, so this inserting the series resistance is not a good efficient method because it wastes power a lot, because that's the armature current that you are impacting. And armature current is relatively a high current, so that's why the best method to really control the speed of the motor is through adjusting the terminal voltage. Based on book, the historical limitation has been that before the last 40 years, there was no practical way to vary the terminal voltage, making series resistance the primary method in older days. But based on modern solutions, we have solid-state power electronic devices that can provide efficient ways to vary the terminal voltage, which improves the speed control procedure. Now, let's go to compounded DC motors. What are they? So a compounded DC motor has both a shunt and a series field. So it combines both characteristics associated from the shunt motors and DC motors together. We have two topologies in here. Basically, here we have a topology which is called the long shunt connection. And the second topology is called the short shunt connection. So in the long, basically shunt connection, you can see that the excitation circuit on the series side would be in series with your armature. But here, in the short shunt connection, the excitation circuit on the series side is coming before the shunt circuit and before the armature. So if that makes sense. Now, in terms of also how the series and shunt fields would help each other out or would be subtracting their effect, we call basically two types of machines, which are called the cumulatively compounded and differentially compounded. So how this is shown? It's shown through the dots here on the field coils, just like a transformer. So when we talked about transformers, we had the dot convention. Here, if basically we have a cumulative compounding that occurs when the current flows into the dots of both coils. So here, if you consider the circle dots, we have two types of dots in here in this circuit, circle dots and square dots. If you consider the circuit dots, so the current for each excitation circuit, each inductance, is going into the dot here for LS, and for LF is also going into the dot, into the circle dot. So this means that the effects of these two circuits, excitation circuits, would be added together. So this is called a cumulative compounding. However, if you look at the basically square dots, you can see that in terms of this LS, the current, the current of this LS is coming out of the series circuit, and for this one, for LF, is going in. So this means that basically their effects would be subtracted from each other. So that's called the differentially compounded motor. So in figure 924, round dots would represent the cumulative compounding, and square dots represent the
differential compounding. Hope this makes sense. Now, let's go a little bit into more details on the circuit. If you write up the KVL for the compounded DC motor, you can see that VT would be equal to EA plus IA times RA plus RS, right? Same thing for here. VT would be EA plus EA times R plus RA times IA. However, for RS, we have IL, which would be different from IA. So this equation 924 would be associated with this long shunt connection. In terms of current relationships, we have IA would be equal to IL minus IF again. So IA would be IL minus IF in both basically long shunt and short shunt connections. The net magnetomotive force and the effective shunt field current would be based on equation 927 and 928. So the 927 equation is telling us the F net, or the net magnetomotive force, would be the F associated with the shunt circuit, plus or minus the F associated with the series circuit, minus the F associated with the armature reaction, right? So this plus is associated with the case of cumulatively compounded, and minus is associated with the differentially compounded case. Now, if you divide basically the sides of equation 927 over an F, you would get IF star, or the basically effective excitation circuit current based on IF plus minus NSE over NF times IA minus F armature over NF, where NSE is the number of turns in the series circuit. Okay, that is also shown in here. And looking at the torque speed characteristics of a cumulatively compounded DC motor, you can see that a cumulatively compounded DC motor has a constant flux component, which would be associated with its shunt circuit. So this shunt circuit has almost a constant IF, unless you change basically R adjusted. Here also, that's the same thing, because RS is relatively small, so this voltage drop is relatively small, which means that VT would be practically falling on basically the terminals here. And this IF is almost constant, unless, as I said, you change that resistance. So that constant flux component is associated with the shunt circuit. The variable flux component, however, is associated with the series circuit. You can see that if load changes, IA changes to a lot of extent. Same thing in here in this circuit. If load changes, this doesn't change very much, but this IA would change a lot. So that's why we have a variable flux component, which is proportional to the armature current. In terms of starting torque comparison, we have a higher starting torque compared to a shunt motor, because shunt motor had a constant flux. But here in the cumulatively compounded DC motor, because of this variable flux component, we have a higher flux compared to a shunt motor. But it has a lower flux compared to a series motor, because for the series motor, we saw that the flux was entirely load dependent. But here is not to that extent completely load dependent. So therefore, we can say that the cumulatively compounded DC motor is a compromise between the two shunt and DC motors. In other words, we are combining the benefits of the shunt and series motors. We are adding extra torque, basically compared to a shunt motor, like a series motor. We do, at the same time, we do not have overspeeding at no load, like a shunt motor, right? So these are some of the advantages associated with this type of machine. In terms of performance variation with load, under light load conditions, we are behaving like a shunt motor. The series basically field has little effect. Under heavy load conditions, we're behaving more like a series motor.
where the series flux would be the significant, basically, component associated with the behavior of this machine. The torque versus speed characteristics does vary with load, as shown in figure 9.25. We should also keep in mind that in practical conditions, we do not have a basically differentially compounded DC motor. So we rarely use that. We never almost use that. We use the cumulatively compounded configuration because of its advantages compared to the shunt and series configurations. There are some cases that if the motor basically converts to a generator, if it is cumulatively compounded as a DC motor, and then now we want to operate that as a generator, it becomes basically differentially compounded now. Under those circumstances, basically, we might get some behavior that we do not want. Now, in terms of the torque versus speed characteristic, if this is a typical, basically, behavior associated with a shunt, and this is a typical behavior, the sharp, basically, behavior associated with a series, the cumulatively compounded would be something in between these two, which has advantages from both, but not completely the same as any of those two individually. Now, in terms of speed control in the cumulatively compounded DC motors, we have the techniques, the same techniques pretty much that we had for the shunt, changing the field resistance, changing the armature voltage, and changing the armature resistance, which is less used because of the disadvantages associated with the losses, same things that we talked about in basically series motors as well. Now let's go to example 9.6. So in example 9.6, we have a compounded DC motor with these characteristics. There are 1,000 turns per pole on the shunt field, 3 turns per pole on the series winding. The machine is shown in this figure. The magnetization curve is shown in here. At no load, the field resistor has been adjusted to make the motor run at 1200 RPM. Okay, the core mechanical and stray losses can be neglected. We want to see what is the shunt field current in this machine at no load conditions. That's the first item. So for this first item at no load, the armature current would be 0. That's what we know. So in the internal generated voltage of the motor would equal VT, right? So if there's no current in here, same VT will fall on EA. Therefore, VT also basically EA must be equal to 250 volts for the terminal voltage. From the magnetization curve, a field of 5 amps will produce basically a voltage of 250. So this is 5, 250 at 1200 RPM. So we said that these curves, magnetization curves, are given at a fixed speed. In this case, 1200 revolutions per minute. Therefore, the shunt field current must be equal to 5 amps. So this is the answer to the first question. And the second question is, if the motor is cumulatively compounded, we want to find out its speed when IA is equal to 200 amps. All right, so for answering this question, we know that we can find out EA based off of this KVL, which gives us a 242. But at the same time, we need to calculate the effective IF or IF star, which would be IF plus NSE over NF, IA minus FAR over NF. So this plus sign is because of the cumulatively compounded effect, which gives us a 5.6 amps, an effective 5.6 amps current, excitation current. Now we go to the magnetization curve, which gives us a 262 volts at 1200 RPM. So at 1200 RPM, 262 would give us a 5.6 amps. So if you go to 5.6 amps, go up, you would get that 260. But this 262. But this 262 happens at 1200. Therefore, to find out basically the speed, the actual speed, we use this same famous equation of N's would be proportional to EA's. So therefore, since our actual voltage is 242, we divide that by the 262 that we got from this curve and multiply that by 1200 to find an 1108 revolutions per minute. So in other words, to answer the question in part 2, part B of the problem, if we are having 200 amps armature current and the motor is cumulatively compounded, the speed would be at 1108 revolutions per minute. Now, part C of the problem is asking if the motor is differentially compounded, when the speed of, we want to find the speed when IA is equal to 200 amps. So I want to have an intelligent guess because we are differentially compounded. So the effective field would be decreasing. So we would expect the speed to be higher than the speed that we found for part B. Let's see how that works. So the solution here is that if the machine is differentially compounded, the effect of the field or the IF star would be IF now minus NSE over NF because of this effect of the differentially compounded, which gives us an effective field current of 4.4. Now this 4.4, if you go to the curve, would give us a 236 volts at 1200 RPM. Therefore, using the same famous equation, N would be equal to EA over EA0 N0. N0 is 1200, 236 is coming from the curve. 242 would be the actual voltage that we got for the machine. In both cases, whether the machine is cumulatively compounded or differentially compounded, basically EA would be the same. It doesn't have anything to do with the field circuit. So in both cases, we have 242. So therefore, from this equation, we find the speed of the motor to be at 1230 RPM. So notice the speed of the cumulatively compounded motor will decrease with load, while the speed of the differentially compounded motor will increase with load. So compared to even the unloaded conditions, you can see that under unloaded conditions, we had 1200 RPM. But now under the differentially compounded motor with load, we have more speed compared to the no load conditions. So keep that in mind also. Now let's go to DC motor efficiency calculations. In DC motors in general, we have the following losses: the copper losses, which could be associated with both armature and field circuits; the brush drop losses associated with the voltage drop across the brushes; mechanical losses, which are associated with the friction and windage; core losses, which are associated with the hysteresis and eddy current losses in the iron core; and stray losses, which are miscellaneous minor losses. So copper losses are calculated using measured currents and resistances. Armature resistance is determined by blocking the rotor and applying a small DC voltage and measuring the current. The resistance varies with temperature and skin effect. So therefore, making the precise measurement and calculation of RA would be a challenge. There are some standards. For example, IEEE standard 113 provides a more accurate method to determine RA. The field resistance is found by applying the full rated field voltage and measuring the field current. The brush drop losses are often combined with copper losses, but they can also be separated. They are determined from a contact potential versus current plot. So the way that it works is that we apply different voltages and get different currents, and through that, basically, we would be able to calculate the VB times IA, which gives us the brush drop losses. For core and mechanical losses, we measure them together as no-load rotational losses. And they're determined by running the motor as rated speed with no load, because under no-load conditions and full load conditions, when you want to compare them, at no load, IA is very small, so the armature copper losses would be negligible. Therefore, the measurements would be mostly associated with the iron losses under no load conditions. And then subtracting field copper losses from the input power would give us an estimation of core plus mechanical losses. So based on the power flow in the motor, all of these basically methods do make sense. Let's go to another example, example 9.8, which is associated with DC motor efficiency calculations. We have a 50 horsepower, 250 volt, 1200 RPM shunt DC motor, which has a rated armature current of 170 amps, a rated field current of 5 amps. When the motor is blocked, an armature voltage of 10.2 volts would produce basically 170 amps of current flow, which is basically rated armature current. And a field voltage of 250 volts would produce a field current flow of 5 amps, which is the rated field current. The brush voltage drop is assumed to be 2 volts. At no load with the terminal voltage equal to 240 volts, the armature current is equal to 13.2 amps. The field current is 4.8 amps, and the motor speed is 1150 RPM. So the first question is, how much power is output from this motor at rated conditions? And the second question is, what is the motor's efficiency? So there are a few basically tests that have been done. The first test is the blocked rotor test, in which we applied basically a voltage of 10.2 volts on the armature exclusive of the brushes. And we measured the rated current, which is 170 in the armature circuit. So this gives us an approximation for RA, or the resistance of the armature circuit, which would be found at 0.06 ohms. And the second basically experiment that we did in here was that we applied a field voltage of 250 volts and measured a field current of 5 amps, which gives us the approximation for the RF, or the field resistance at 250 over 5 equal to 50 amps. Therefore, at full load, which is the case that we have 170 amps in the armature circuit, the Ri2 losses, the armature Ri2 or copper losses would be 170 squared, I squared times R, which becomes 170 powered by 2 times 0.06 ohms, which becomes 1734 watts. And the field circuits copper losses, or Ri2 losses, becomes 5 powered by 2 times 50, or 1250 watts. And we also have brush losses. We assume that the brush voltage was 2. So P of the brush would be VBD times IA at the rated basically conditions of 170 amps in the armature. That would be 340 watts. Okay. The rotational losses at full load, the rotational losses would be essentially equivalent to the rotational losses at no load. Since the no load and full load speeds of the motor do not differ too greatly. Okay, so this is also one type of assumption that we make in these types of experiments. This means that the no load armature input power would be equal to the rotational losses, practically speaking, because under no load conditions, IA would be negligible. So P rotational would be P core plus P mechanical. This is the addition of P mechanical and P core. That would be called P rotational, which becomes 240 times 13.2 amps. And this is coming from the fact that at no load with the terminal voltage applied at 240, we would get the armature current of 13.2 amps. So this gives us that estimation or approximation for P rotation. Now let's go to part A of the problem. How much power is output from this motor at rated conditions? The input power of the motor at the rated load would be just VT times IL, or 250 times 175, which gives us basically 43,750 watts. And the output power is given by basically input power minus all of these losses that we approximated, which becomes this 43,750 watts minus all the losses, P brush calculated in here, PCU calculated in the addition of these two, the summation of these two, core plus mechanical losses that we call that P rotational, and we assume that's 3168. And this is the basically 1% assumption for the stray losses, which are called the anonymous losses. So stray losses are taken to be 1% of the input power. So whatever the input power was, we approximate the 1% of the input power would be your stray losses. So we're going to use this to find out in part B the motor's efficiency. Of course, all of these basically percentages, if given in a problem in exams, would need to be given to you. That 1% approximation associated with the stray losses, for example. So based on this, these losses, the efficiency of the motor at full load would be P out over P in times 100, which becomes 84.2%.